Hello everyone, can you hear me? Yeah, I guess you can. My name is Tommaso Cecchi and I'm going to present you with the bus buffer idea of DDN product, which is Infinite Memory Engine, or IME. By the way, you will be hearing about it in the afternoon as well from Hussein from CSCS. He will probably speak more about the tests he's been doing. I will present with the basic idea of the product and the technology. And anytime of course you interrupt me if you want to know more. We can even discuss with questions here or offline. Now, IME, Infinite Memory Engine, is a development effort started more than 2 years ago. It started in DDN when not only DDN, but was starting to discuss about bus buffer technologies. And the idea and the assumption under which this product, this technology has been developed is that in modern HPC architecture, you don't have a steady flow that goes from your computing resources to the storage area. So there are many studies that instead show that the flow of data is most of the time a very low flow, and then you have spikes that burden the capability of your storage system. This is there's an important study from Agro National Lab that shows that in a time frame of 3 months, I think, the overall application portfolio was just using I will show it later, was just using a very small amount of bandwidth towards the storage area, while only in a limited amount of time the bandwidth was used at 70 or more %. Now, one problem of this is that when you have to provision your computing resources with a storage area, you have of course to put a storage area which is capable to satisfy the needs of the most greedy and the most I/O hungry application. Otherwise, you would have computing resources waiting idle for the I/O to be completed. So that means that you will, by design, provide computing resources with something that is more than needed for most part of the time. That has several consequences in terms of cost. Of course, the purchase of the system, but it's not only that, it's that you have to power and you have to cool down more stuff than you most of the time need. It's not just about performance, though. In fact, the easiest way we have in current storage architecture to improve the bandwidth is by increasing the number of spindles. That means that if you want to add performance, you have to add spindles. Hence, you have to add capacity. That means that you have a very hard binding between capacity and performance. So more you will spend in capacity that you don't need. So the idea of the IME and the bus buffer technologies is to be right in front of the computing resources and in front of the parallel file system as well, in order to absorb the spikes and decouple performances from capacity. So you have all your tasks that you want to accomplish, and you want to, through the interconnect, which, as we saw before, it's most of the time InfiniBand, but in principle can be anything. And then you want to use as a unifying layer this bus buffer technology to intermediate the communication between those tasks and the parallel file system. So that is actually the position of IME. Now, of course, as you can imagine, this product is based on the modern, on the fastest NVM devices, so SSDs mainly. But it's not just about that. Actually, the real value of the product is not in the hardware, it's more on the software. I want to quote what Tony Cortez was saying before, and he was saying traditional file systems are not the right abstraction layer for NVM devices. That's exactly the idea of IME. So the idea is that to leverage these devices, you have to completely change the approach towards the storage organization and storage management. So you don't want to use the usual POSIX layer, even though we will see we cannot escape completely from it, but you want to use a different approach. Now, basically, this is what we were talking about a few minutes ago. Now, the point is the following: one of the problems that we are seeing, it's very common to see, is that even in HPC architectures, where we know that most of the applications are doing large-sized I/O, sequential streaming, even there we suffer when we go to small-sized I/O. When we go to 128K or 6432 or even lower I/O size, in those cases we start suffering for higher latencies and poor bandwidth. Now, the problem is not something that you can tackle by just putting a bunch of SSDs, because the problem is not only on the hardware side, it's also on the way the file systems manage this kind of traffic toward the storage area. So IME tries to address this problem in 3 different ways. So, for example, one thing that IME does, let me go back. One thing that IME does is that anytime it receives this layer, anytime it receives I/O from the clients, no matter how the I/O is formed, so no matter if the application is writing at 32 kilobytes or 1 megabytes, there will be some coalescing of I/O internally in the IME servers that will, in any case, deliver towards the SSDs a 1 megabyte I/O to the SSDs. In this way, of course, we obtain couple of benefits. Of course, one is pure bandwidth. We know that even on SSDs, the higher is the I/O size, the better is the bandwidth. The other thing is that we don't pay the penalty in terms of all the operations that the SSD controllers need to do in order to limit the write amplification problem. So we know that the erasure block must be wiped out before it can be rewritten. So by writing this large I/O size, we also increase the lifetime of the SSD. So we try also in this way to be more SSD friendly, hence increasing the SSD lifetime. Another way we try to eliminate the problem of small I/O size is by removing one of the paradigm that is pretty common in all the shared file system, which is the management of locks. So whether you use GPFS or you use Lustre, anytime you have to write a file, you need to get a lock. This is because you want to avoid that another process accessing the same directory or the same file can result by accessing the same area in some unpredictable outcome. Now, that means that you have to implement a lock manager function, which is MDS on Lustre, and which is the file system manager and lock manager in GPFS. And that means that even if you don't need this kind of management, because you know that your application will never contend the area with other applications, even in that case you pay penalty. And when the I/O is small, that penalty will be visible, will be pretty visible. Now, one of the things that IME does is that it removes the need of locks. So it is, as we call it, a lock-free architecture, where it is left to the application side to manage this kind of contention. The idea of this is that the application, of course, knows better when this is needed, when this kind of management is needed, and can implement this kind of things only in very specific area of the code. This allows for IME to, I think it's the next slide. This allows IME to have better performances even in small I/O. So this test is has been done on one 4 IME servers configuration. So we had 4 IME servers where we were running IOR benchmark from 8 kilobytes I/O to 4 megabytes I/O, and we are seeing that the performance is pretty flat as the I/O size changes, which is not the case. I think this case was with Lustre, but it shouldn't be much different with GPFS. Now, the importance here, honestly, is not this difference. The importance is the different shape of the two, because of course here I could have put more disks on Lustre and I could have had even higher performances than IME. The point is that I will still have this drop in performance when I go to smaller I/O size. And this is pretty irrelevant how many SSDs I can put, because this is something intrinsic in the file system protocol. Another way IME tries to address the problem of small I/O size is the following. Now, anytime in modern storage architecture, I would say pretty all of them, anytime you do a small I/O, if you implement any kind of RAID, you have to pay the rate modified write penalty, which is something that you have to do because usually the RAID is a fixed size. So if you're writing an amount of data which is smaller than the write size, then you have to arrange the parity and the blocks inside the write stripe. Now, IME tries to tackle this by moving this function from the storage server or the NSDs or the OSSs to the clients. So the point is that the RAID formation, the RAID group formation and management, and the parity calculation is moved from the servers to the clients. So for example, one thing that the client can do is decide to we call it adaptive RAID. So one thing that it can decide to do is to send to the servers a RAID group which is made only with 128 kilobyte write size, or 64, depending on how much data the client needs to write in that moment. The parity calculation is done on the client server as well. The idea is that on a normal installation, you have 4 NSD servers or 4 OSSs, 8, 16, 32, and you have thousands of clients, which typically have more CPU and more memory than the servers have. So it's pretty logical to delegate some of the tasks to a broader range of clients instead of going and realizing actually what is a bottleneck to the servers. So that is how IME tries to address this. What we are seeing are the most urgent problems in the I/O on HPC. So this is another thing I didn't mention. So this is a typical workflow where we have the compute clusters, we have IME bus buffer, and we have the parallel file system. Of course, the fact that we are using IME does not prevent the application to access directly the parallel file system. We might think of problems or of applications where the benefit of IME is not something that you want to have. Well, for example, if I have an application which, differently from what we said before, has an I/O flow which is steady and would tend to fill up the IME cache, then in that case I probably don't want to use IME. Anyway, what we are seeing, so in this case we see a lot of bandwidth between compute cluster, and instead this was a case with an application, a fluidodynamic application, if I don't go wrong, which was using a small size I/O 4K, and the file system was performing very poorly. Now, it's not important this number per se. The important thing is that the same amount of data, when flowing through IME, not only was able to be written faster than it was to the file system, but even when IME was flushing data to the parallel file system, I was able to get better performances than going directly to the parallel file system. The reason for that is because IME actually, instead of acting as a bare pipe between the compute clusters and the parallel file system, it actually does some reordering of data and put it towards the parallel file system, in a more friendly way. So, for example, it tries to coalesce contiguous extents of data in order to minimize the randomness of I/O and to increase the I/O size. Yes, this is, I won't spend much time on this. This is a comparison on a test that we made where we were trying to achieve the same level of performances, of capacity, with only SFA, which is the traditional block storage, and SFA and IME. So one of the thing that IME is peculiar is it's a very dense appliance. So we have the appliance and we have the IME server. Well, we can have a lot of gigabytes per second in a very limited amount of rec unit. We'll see a bit later on about this. Now, I want to introduce a bit how the software stack, the IME software stack, sits compared to the other I/O layer. So this is one typical description of the several I/O layer that you encounter from the application side to the the storage. Here you have the RAID, and here you have the VFS on Linux, and then you can do a POSIX IO or MPI IO, or even higher level library IO like HDF5 and NetCDF and so on. Now, IME, in terms of this, will simply sit here, kind of replacing this layer and offering more or less the same interfaces towards the application, with the difference that it gives the opportunity to bypass all of these layers and directly interact with the application. So we will see that IME gives basically three ways, three interfaces towards the application. Okay, basically, here I have IME native client library, and then I have the possibility to directly interact with the application. What does that mean? So the application will do some write, some read. If it needs to interact with IME, we'll instead call native IME library. So it will do IME read, IME write, and so on. This is something that is, of course, very intrusive in terms of application development, because you have to rewrite or write from scratch your application, or just the part of the application that does I/O. So probably this is not something that will be broadly used, but is important because in case you want to, it's there, and of course it gives you the most direct access to the IME layer. The other way you have to interact is something that is very common, of course, in the HPC cluster, which is the MPI/IO interface. So what you would do in that case, you will build the MPI/IO environment, linking it and building it with the IME libraries. And then what you would need to do is just recompile your application, linking your application to the new MPI/IO environment. And by this, anytime you will do an MPI file open, MPI file read, you will actually invoke IME libraries through the modified MPI/IO layer. That means that on the application side, the only there's no change required in the code. The only thing that you would need to do is recompile the application. And last but not least, the Fuse interface. Of course, as I was saying before, we cannot escape from these. So we are providing a POSIX interface towards the application through Fuse. In that way, you will access IME by simply doing the standard I/O call, like read and write. These are most probably mentioned in terms of invasiveness. So the first one was most invasive in terms of changes required to the application, but it's probably the faster way to access IME. And so on. So now the difference is not much. So benchmarks are showing that we see, say, the performance of direct access, and Fuse is showing something between 70 and 80%, even more. So it's not a great penalty if you consider that you won't need to change almost anything on the application side. Yes, that's what I've just said. Before I finish, a bit of the internal architecture of IME. Another thing which is peculiar of IME, it's not unique, but I would say that in the other solutions we've studied, it's rather peculiar, is the way IME places data on the storage infrastructure. So take GPFS or Lustre. In order to maximize the benefit of having thousands of drives or tens of OSSs or NSDs, what you want to do is to use all the single components. So you will adopt a round-robin strategy, which means that you will send 1 megabyte I/O to each NSD servers or OSSs, and in turn the OSS will write the same amount of data on each OSD, and so on. Now this is good. This is good because every single component will be involved in the I/O and will be involved in the same way. So you will get the most out of it. Point is, as you have bigger and bigger infrastructures, the likelihood of having one of these components misbehaving or being involved in some rebuilding operation is more and more likely, is higher and higher. So the point is that when one of these components start to go, say, at 50% of its maximum capability, that means that the overall infrastructure will go at 50% of the performance, because you won't be able to send the 1 megabyte chunk to the healthy NSD server unless the failing component has completed the write or the read of the 1 megabyte chunk. That is, of course, bad in big infrastructures because the likelihood is higher, but it's bad also because the impact of this bad component is higher. So if you have 10 NSD servers and one of those is going at half of the performance available, then you would lose 5 equivalent NSD servers. Now, I will go back then. Now, this is a test that we made on several IME servers. So what we were doing here is that starting with 2 IME servers, we were writing data. Then with 4, 6, and so on. Then what we were doing, we were injecting I/O on one of these IME servers. So we were putting some external I/O source in order to mimic a faulty component or a component which was misbehaving or going a bit more slowly. And then we were doing this test with 2 data placement strategy. So by default on IME we will use what we call it the non-deterministic approach, while the deterministic is the round robin I was talking about before. So here is referred to like deterministic and heuristic. Now here I have 2 lines, even if well, probably you can see those. I have 2 lines here, and these are the performances that you see when all the IME servers are behaving okay. And so I have the data placement strategies which are equivalent here, of course, because all the components are okay. Now, what happens when you start to impact one of these IME server? Well, of course, let's say that you are reducing a lot the performance of one IME server. Of course, here you will have more or less a 50% drop in performance. Point is that when the number of IME servers increase, then you will have, on the, call it deterministic approach, you will have the impact in terms of this difference, which increases as the number of components increases. While if you use a non-deterministic approach, this reduction is fixed because I will tell you what this non-deterministic approach is. So the idea is that IME keeps a latency table. So anytime a client ships data towards an IME server, it records in a way the latency it took to receive and acknowledge of that I/O. With this table, the client is able to deliver the data according to the status of the overall infrastructure. So if I have an IME server for whatever reason which is responding slower, then I will send that IME server less data. I mean, at the limit, I won't send any data at all if it's so slow. So that means that instead of propagating the problem towards all the components, I will isolate the problem to the failing device. And that benefit is something you can appreciate, of course, the bigger is your infrastructure, because the difference between these and this will be bigger as higher is the number of components involved in your I/O infrastructure. I wanted to. This is another way of seeing this. So what we were seeing, we were doing some I/O on IME servers, and then we were injecting some external I/O. So we were seeing here we had, I think, 4 or 5 IME servers, and so we were seeing with the deterministic approach, we were dropping performances up to almost 50%, while here the reduction was really less than that, because of the non-deterministic or heuristic approach and data placement strategy. Okay, so let me go back here. This is, oh, yeah, 0. Okay, so just this last slide. This was a test where we were running an application which was doing checkpoints to the parallel file system, actually to IME. So what we were doing, we were running 3 checkpoints and then flashing the last of those checkpoints to the parallel file system. So one of the good things is that we were able to see better performances. Here we are at about 4 or 5 gigabytes per second, which is something not very easy to achieve when you're writing at 4K. The other benefit of the bus buffer technology is that in this way, those 2 checkpoints will never reach the parallel file system. You will just preserve the last one, which is the one that you need in case you have problems and you have to restart your application. But this will not be used at all and will not impact your parallel file system. Now, I think I've run out of time. The only thing I want to mention, and it is the takeaway, I think, of this brief introduction, is that one thing of IME is that it gives you some very important features now, because you will have the ability to reach a lot of performances in a very small form factor. But the important thing is that by discarding the important paradigm of POSIX approach and traditional file system, we see a very long-term roadmap that will allow us, we think, to achieve even better and more effective solutions to our I/O problems in the HPC we're seeing today. Thank you.